First, I just want to start by welcoming everyone to the first opening session of Soil School. This is our 10th annual Soil School, which is really cool. And, it started, James and I were just talking, started at a small little rental space in Northwest Portland back in 2012. And here we are 10 years later, still talking about soil and still getting excited about it. So it's always, always a fun part of the year for us. I'm Scott Gall. I work for West Multnomah Soil and Water Conservation District. We are hosting this webinar series with our partner, Tualatin Soil and Water Conservation District. Christina is my co-host tonight, and she's from Tualatin SWCD. West Multnomah's mission is to provide resources, information, and expertise to inspire people to activity, improve air and water quality, fish and wildlife habitat, and soil health. We serve residents of Western Multnomah County, including Sauvie Island and a portion of the Bonnie Slope neighborhood, with conservation planning, weed management, native plants, wildlife habitat restoration, and school and community gardens. Tualatin, with a similar mission, is to create a sustainable, productive, and healthy environment for Washington County, Oregon community. They serve the residents of the county by providing educational opportunities, advice about natural resources conservation, and financial assistance for conservation. Of course, if anyone wants to get in touch with either district, if you're within our district, feel free to reach out. Also, there's probably folks joining from all over. And if you have any questions for your local conservation district, we can, of course, help put you into contact. I want to start by welcoming everybody. I mean, this is the start of an 8-part soil series that'll be every Tuesday and Thursday night through the month of April. And the turnout is always amazing. And I just want to start by just welcoming everyone. And I want to take a moment to formally welcome all of you to this workshop. I want to welcome you if you're totally energetic and jazzed to be here. James is. I also want to welcome you if you're feeling distracted by other things going on in your world. I want to welcome you if it's the first time at Soil School, or welcome back if you've been here and done this before. Welcome to those just beginning to learn about soil, and to those soil geeks out there that might know what isomorphic substitution in clay means. And yes, soil journey is really that wild and crazy. Welcome if you're Indigenous American, African American, Asian Pacific American. Welcome if you're from a Latinx background, or if you're European American. If you're some combination of the above, or if you're none of the above, welcome. Welcome to all our female participants and the males. Welcome if you're trans. Welcome if your gender expression is beyond the gender binary. Welcome to the farmers, the gardeners, the ranchers, nature explorers, the educators, the students, the conservation professionals. Welcome to all of those who love soil or soon will, because there's no one else. Welcome if you know exactly why you're here. Welcome if you don't. Welcome to the sad, happy, angry, hopeful, desperate, and silly parts of all of ourselves. And welcome to anyone that feels that I've left them out. And please feel free to let me know, because I want to establish a very welcoming environment we're all here to learn about soil and what we can do to better the soils around us in the land. I also want to take a moment today as we gather to talk about soil, all that soil does to benefit us, and all we can do as stewards of this land to better ensure its long-term care. As we discuss these topics, it's important to acknowledge the important stewards, the Indigenous people of the land, as we focus on it, and their deep and extensive knowledge of this land. In my district, West Multnomah, I want to specifically honor the original Indigenous people of that area, the Clackamas Chinook, the Willamette Tumwater, the Wasco Wishram, the Watlata, the Multnomah, and the Chinookan peoples, as well as the Tualatin Kalapuya, the Cayuse, the Molalla, the Yakima, and other tribes and bands of the Willamette, the Columbian Willamette River, and to the tribes beyond, the original people of the lands where you sit now. We wish to honor them by committing to the work with their descendants and learn from the traditional ecological knowledge and relational worldview of the land and all things upon it. We further recognize we are here because of land displacement, attempts at cultural erasure, and other sacrifices that were forced upon them. We remind ourselves that we are guests of this land. We must do our best to honor the original peoples through authentic cultural narratives and continued caring of and giving to the air, water, plants, animals, soils, and ecosystems of this land. To follow this acknowledgement with action, we will pursue impactful partnerships with Indigenous people, tribes, and their sovereign governments and intertribal organizations. And from what we learned here today, we hope each of you will take home the importance of reciprocity with the land, as we take what the land provides us, we also give back to the land as mutual benefit. Now, I would like to go over just a few really quick housekeeping tips for you, sorry. And then I'll kick it off to James, because that's why we're all here today. Again, we're recording this session. We're recording all 8 sessions of Soil School. They will be available on Tualatin's YouTube channel by the end of the month. Christina will put that in the chat, I believe, and the link to that. So you can either go see this talk again if there's a part you want to come back to, or if you want to see some of the following in the future. Tonight's presentation is about 1 hour and 15 minutes. With about 15 minutes for Q&A. If you put your questions in the Q&A, not the chat, if you see a question you like, you can upvote it by clicking a thumbs up icon in the Q&A window, and that way we can kind of rank, where most people are interested in the same question. And then finally, we have a survey, and we want to know what you think about tonight's session. We'll be adding that link in the chat window as well. And then from there, I'm going to now kick it off to James. Thank you, James.
All right, hang on. Here I am. Hey, how you doing? Thanks again. What is this? I don't know, 7 or 8 times. Hey everybody. Thank you for inviting me. And I think this is my 7th time doing this. I do this for these cups. I don't know if you know this, but they give me these West Multnomah steel tankards, and this is the old logo. So that's why I'm here. Actually, the reason we're all here is because of soil. That's a fact. And it won't be long now, and we'll all be, well, back to normal soon enough. My name is James Cassidy. I'm a senior instructor at Oregon State University, where I teach introductory soil science classes, the big classes, over 100 students. And I also teach soil management for organic production, which is a 300 level class, a really in-depth look at managing organic matter and some nutrient management, etc., and soil health. And I also teach an organic farming and gardening class, which I'm teaching right now this term. A lot of work. And I founded and am the faculty advisor for the OSU Organic Growers Club, which is a student farm here on campus. And I've been doing that for 22 years as a volunteer myself. And the project has grown. We now have multiple acres. We have an organic cherry orchard. We have organic grapes and blackberries and strawberries, as well as all these different vegetables. And we sell all those to fund the student farm project. And that's completely self-funded, no support from the university, other than they don't try and throw us off anymore off the land, although we are squatting on the land. So, it's land, land is your land, this land is my land. And the students have been coming out for 22 years now. We feed them hot supper every Thursday night for the last 22 years. Anyway, what I want to talk to you about is about soil. That's what it's all about. I mean, it's all about soil. I mean, everything. I don't just mean like growing food. I don't just mean like forests and all that stuff. I mean, everything. It's all about soil. I mean, maybe you never thought about this, but every atom in your body has been through the soil system billions of times already. I mean, think about that. You live, you die, we live, die, things live and die and live and die. And they're all cycling through the soil as they have done billions of times before. The fact that you are not soil at this moment is a temporary condition. And most of the time you're like, soil, and then you're coming up for a day, the spring, before you know it, it's back to normal. And it won't be long now, folks. And I don't mean, and it's almost over. And I'm not talking about this talk. I'm talking about your life. I mean, this is just for this amazing moment right now. Here we are together, just for the heck of it, 6 o'clock in the evening via this technology to talk about something so fundamental and to talk about and if you're here, I mean, again, I love this audience because this audience is already like thinking about soil, probably does a lot of gardening, probably interested in this stuff. And so this is like just a choice group for me to speak to. And I'm very honored to be here. But actually, every atom in your body was once inside of a rock. I mean, I don't know, I happen to have some rocks here. Here's some rocks. Look at these different kinds of rocks. And you can see that rocks, what a rock is made out of is different crystals. If you look at this up close, you can see these different colored crystals, kind of yellow ones, orange ones, white ones, and black ones. And what those crystals are, those are different minerals. And a rock is just a collection of minerals. And these minerals are actually crystalline forms of different elements in the Earth's crust. And there's like, 118 elements, depending on how you count, right? But that's where all this stuff came from. I mean, everything in this room, every person you've ever seen, everything you will ever experience ever on this planet Earth, it's all made of the same stuff. And it's these 118 elements, depending on how you count. Yeah, there's a bunch that only last a billionth of a second, but still the ones that are here in the moment right now, that's what everything is made out of. Every atom in your body was once inside of a rock. And what soil is kind of like rotted rocks in a way of thinking. They kind of fall apart, and these little granules that we call sand, and then there's silt, and then there's really tiny ones called clay, different size particles. And what these, maybe you've never thought about this or ever knew about this, but rocks dissolve in water. They dissolve in water. And most people, they think, what are you talking about? Rocks? That's why we build things out of them, because they don't last forever. They're actually quite unstable at the surface of the earth, rock is. And if you don't, and if you don't believe me that rocks dissolve in water, here's some table salt, a little bit of sodium chloride, which is just a mineral, sodium chloride, right? It's two elements. And it's actually the only a table salt is the only mineral that we actually eat directly. But if you look at this, you put a little bit of this, and if you don't believe me, just do this. Put a little bit of table salt on your hand and then lick it. It's dissolved. It just dissolved. And that's an example of a mineral that dissolves very rapidly. And some minerals dissolve fast and some minerals dissolve slow, but they all eventually dissolve. And so look, here's a rock. And if I put a little bit of water on it, you see that? It's dissolving right now, really. Right now, a tiny bit of that mineral, of some of these minerals have dissolved away. And the first thing to dissolve out of a rock are the salts. So some of these minerals are salts, and the salts dissolve out rapidly, and then they move down. And imagine this, if this was on the surface of the soil, and I've dissolved a little bit of those salts out, and those salts moved down into the soil, and it rained a little more, and it went a little deeper, and it went a little deeper, and it went a little deeper, and it went a little deeper. And eventually, every time it rains, it goes a little deeper, and that salt continues to migrate down, and eventually it gets to the water table. And once that salt gets into the water table is connected to the creek underground, and the creek is connected to the bigger river, and the big river is connected to the giant river, the Columbia, and the giant river flows into the ocean, and that's why the oceans are salty, right? And the next thing to dissolve out is the molybdenum, or the potassium, or the phosphorus, or the cobalt, or the whatever is in here, all those elements. And different colored rocks have different nutrients, and those are what are called nutrients. And all of the nutrients dissolve out of the rocks, and they eventually move down into the soil and down it, and they eventually get in the water, and they eventually go to the ocean. And that's why they're sharks, because the nutrients flow off of the land when the rocks dissolve, and they end up in the ocean. And that's why there's life in the ocean, is because the nutrients ended up there. And what What soil is somewhere between all of the nutrients being locked up inside of a rock somewhere and dissolved and all the way out into complete dissolution into the ocean somewhere. And in either case, those are not available to plants. Plants can't eat rocks, right? And plants can't get the ocean water where they are. So somewhere in between is this moment where the rocks are sort of dissolved and the nutrients have been sort of released and they're in the water and they can be taken up by plants at their roots. And the roots pull that water, and that's how the nutrients get into the plants. And then you eat the plants. Or your mom ate the plants, right? And then inside of you, that is biodegraded by the bugs that live inside of you, and they release those nutrients and they go into your bloodstream. And by the instructions of your DNA, which is itself, DNA is made from dissolved minerals to store that data and that information so that you can build the tissues of the body. You know, that's what I mean when I say it's all about soil. Every moment of your existence from cradle to grave is dictated by the reality of that. The reality that rocks dissolve in water and release nutrients that plants can take up and fix into their tissues. Okay, so and there's different kinds of rocks that have different minerals in them. And so there's different soils all over the place. And in fact, I happen to be in the teaching lab here at Oregon State University. And I want to show you, just as an example, if we go over here, you can see all these different kinds of soil, right? And so there's actually 20,000 different named soils. And I've only got about 40 of them here. And you might recognize some of them because you might recognize them as being locations like the Newburgh or the Dayton or the Chehalis, Amity, right? Willamette. These are named soils. And some of them are pretty thick and some of them are quite a bit thinner. Like over here, these are the Eastern Oregon soils. And if you look at this up close, you can see this layer down here? That's actually salt because the water never gets to the water table because it doesn't rain that much. And more on that in just a moment. But I just wanted to show that to you just briefly so you can kind of get your head around this idea that there's actually a lot of different kinds of soils. 20,000 different named soils in the USDA system. And that's because they're made of different rocks and under different climatic conditions. Okay. And one more thing, I just want to show you one more thing. I'm going to switch to another camera here. Here's an example of some different soils. This is actually Jory soil. And Jory is our state soil. I don't know if you know we had a state soil, but we do. Let's see if that'll automatically focus there. And that's because the last thing to dissolve out of the rocks, all of the rocks will dissolve away except for the iron, which actually becomes iron oxide, which is rust, which is the most abundant element in the Earth's crust, is iron. And when the rocks dissolve and the iron dissolves and it recrystallizes at the normal surface temperatures and normal surface pressures at the surface of the Earth, it becomes rust. And that's why we have these red soils up in high elevations. We'll talk about more of that. Look at these soils up close. If you look up close, you can sort of see these tiny little holes, and you can see they're made of individual grains. And these are just clumps of soil that are clumped together. We call those aggregates. And you can see there's light colored minerals in there. And these are different soils. And look at this one over here. This is an ashy soil from Eastern Oregon. So really different soils in different places because of different kinds of rocks that produce them and in different climatic conditions. All right. So we got to talk about something else. We talk about rocks. We talk about where nutrients come from. And that's what it's all about, right? I mean, that's what fertilizers are. They're NPK, all the macro and macronutrients and all that stuff. They all came originally from rocks. But we got to talk about the other side of this. And the other side of this is, and look at this, here's some soil. I happen to have some right here. check this out. It's got living material in it. And the roots are down underneath on the underside, right? Now, I don't know if you know this, but in a single pinch of soil, here's a single pinch of soil, there are over 1 billion living organisms in there. 1 billion living organisms in a single pinch of soil. I dare you to forget that. I dare you to remember that. In a single pinch of soil, there are over 1 billion living organisms. And it's not just a billion of one thing, tens of thousands of different species in this pinch of soil. Tens of thousands of different species. And 99.99% of which we don't even know who they are or what they're doing. You're like, what are you talking about? Why do we only know 0.01%? Because only 1.01% of these will actually plate up on an agar plate. The rest of them will die if they do that, because they need to live in a society, in a culture, in a community of organisms, where one is like mutualistic and beneficial relationships and antagonistic relationships and predator-prey relationships. You can't even imagine what's going on inside of here right now. And there's billions in a single pinch. And so soil, if you get nothing else out of this talk tonight, soil is a living thing, a single pinch of which has over 1 billion organisms in it. And I challenge you, I dare you tonight, before your head hits the pillow, to get down on your hands and knees outside in a private moment and pick up a pinch of soil and just look at it and say, 1 billion. And just try and get your head around that. Just try and get your head around that. And they've always been here, and they always, at any soil you ever will encounter ever again the rest of your life. This is what's going on. If you get nothing else out of this talk tonight, soil is habitat. It's habitat. By any measure, the most diverse habitat on the planet Earth. You might think, what about the oceans? Aren't they super diverse? No. You take a pinch of seawater, it's about the same temperature, it's got about the same nutrient content in it, it doesn't have any air in it, so it's half as much, there's twice as much habitat in here, because half of this is space and half of that space is either filled with air or water. That's 2 habitats. Plus it's in contact with the nutrients itself, which is the rock, and the rock is dissolving. And there are just all these different habitats inside of this soil. And if you get that, if you understand that soil is a habitat, then you know what to do to it and what not to do to it. And you can derive a lot of the rest of it yourself just by understanding that basic fact. But so that's what soil is. Soil is a habitat, right? It's another thing it is. But look at this stuff. You see this stuff? These are plants. And this is kind of, look, I have a rose here. Look at that little rose. And what is that made out of? I mean, what is this grass made out of? And if you say soil, you're usually right when you say that. But in this case, what plants are primarily made out of? They're primarily made out of carbon. And where does the carbon come from that makes a plant or a rose or a root or a tree or any of that? Where does that carbon come from? It comes from the atmosphere. Because plants, they don't breathe the atmosphere. They don't breathe carbon dioxide, which is where the carbon is, right? In the atmosphere. It's invisible. Sorry, you just got to believe me. Okay? There's carbon dioxide out here. And plants, they don't breathe carbon dioxide. They eat it. They eat the atmosphere. And they take in carbon dioxide, and they take that carbon dioxide, right? It's a compound. And and they take it apart, and they put it together into tissues like this. So they take the atmosphere, they take it apart, and they put it together into tissues like rose petals and stuff like that. And that's what a plant is mostly made of, is carbon from the atmosphere. And in order to do that, in order to take the atmosphere apart and put it together into wood and tissues like that, it's an endothermic chemical reaction. It's just a chemical reaction, okay? It's an endothermic chemical reaction. And an endothermic chemical reaction requires energy input. Think about it. To take something apart, put it together, requires energy. And where does the energy come from that these plants are using to do that? Where does the energy come from? Come on, gardeners. Think about this. If you go out and look outside right now, right up there, there's the sun. The sun shines down 93 million miles away. There's a star out there that's giving UV radiation to this planet. And plants have figured out a way to capture that energy in their chloroplasts. And some of that is a little bit of a mystery, to be honest with you still, how that actually works. And they can take that, and those photons knock an electron into a higher orbital. When it drops back down, it releases a tiny bit of energy. And that energy is captured in ATP, which itself is a chemical that stores that little bit of energy from the sun, and that goes to different parts of the plant, and it's used to take apart carbon dioxide, to put it together into tissues, to take it apart, to move things around, to build those tissues. And that's being, and that's where the energy comes from. It's almost like we live in a giant solar system. You know what I mean? Like we're like orbiting a star, and that we are, right? And the energy of that photosynthetic product inside of these tissues right now is the energy of the sun at the time of photosynthesis. At the time this was made, the energy is in this. And if you don't believe me, I mean, look, here's just a tissue, right? Look, here's a piece of wood, right? And if I get this wood to 451 degrees, you know what happens to it? It burns. And what is burning? It's the energy inside of the wood is being released that came from the sun at the time of photosynthesis. So if I get this piece of wood to 451 degrees, it burns. And look, it keeps burning because now it's overcoming the activation energy necessary for the oxidation reaction, the exothermic chemical reaction, right, to occur. And look, did you notice? It kind of went, look, it's going away. Where is that tissue going? I mean, that tissue was just a piece of wood, right? And look, it went away. Have you ever noticed that when you're burning in a fireplace, right? And the wood just kind of melts away? Where is it going to? It's going back to CO2, water vapor. And the heat is the energy that's being released that was captured in the photosynthetic bonds of those tissues. And what's left over after it's over? Look at, what is that stuff? What's left over in the fireplace after you've burned the wood? That's ash, right? And what is ash? Ash is the mineral nutrients. The minerals that were taken up by the plant, they don't burn. They're minerals. The CO2, the wood is mostly made out of carbon, goes back to CO2. And that's the carbon cycle, right? Most of you know that, but maybe you really never thought about it. So next time you're sitting in front of a fire and it's crackling away and you're feeling that heat and you're seeing that light, what you're really experiencing is the energy that was harvested from the sun by plants that live in soil. And it's not just happening there, folks. It doesn't just happen in a fire, folks. It's happening inside of you right now. You want to know what the answer is? Doesn't matter what the question is. Do you want to know what the answer is? The answer is add organic matter. Everybody say it. Add organic matter. Doesn't matter what the question is. The answer is add organic matter. Because when you add organic matter 3 times a day, you do it if you're lucky. You add organic matter, what you're adding is carbon and energy. And you know what? The billions in a single pinch, you know what they eat? They eat the same thing you do. We can't sit out in the sun and get energy from the sun, and we can't eat the atmosphere. So what do? We eat these plants, and we eat them, grass or not, whatever. Oh, right? And what I just did now, look, I hope this isn't a big shocker, but there's a hole here, and then there's a hole here, right? And there's a tube going through your body, right? And that's the outside world that's inside of you. And this hole is connected to that hole through a tube, and it's a separate world. It's the outside world. And you know what's inside of your gut right now? The same bugs that are in the soil. The soil is inside of you. You're carried around in this tube inside of your body. And what do? You take organic matter, you put it in there, and you know what happens? The billions in a single pinch are in your gut right now, and they ooze out enzymes. And here's what happens. God, hang on, I couldn't get that one down. Ooh. What happens is if you were to take this little matchbox made out of cardboard, which is made from a tree that grew in soil, and if I were to light this on fire, it would go back to CO2, water vapor, heat, and ash, right? What if I took this little box and I buried it in the soil? What would happen to it? It would decompose. And why is it decomposing? Because the soil is eating it. And what does the soil do? The bugs, the billions in a single pinch, what they do is they ooze out enzymes, and all enzymes are chemicals that lower the activation energy necessary for the oxidation reaction to occur, to burn at a lower temperature. In fact, they burn, things rot through the winter at those cold temperatures. And have you ever noticed how rotten wood just kind of goes away? It's going away for the same reason. It's going back to CO2, water vapor, heat energy. A tiny bit of it takes a long time. It doesn't happen all at once. And what's left over is that's what happens in a compost pile. Have you ever made compost? Sure you have. What happens? It gets hot. Why does it get hot? Where's the energy coming from? It's coming from the carbon to carbon bonds being broken by the enzymatic action of the billions in a single pinch that are living in that compost, that are oozing out enzymes, lowering the activation energy necessary for the oxidation reaction called burning to happen at a normal temperature. And that's what's happening inside of you right now from the food that you ate. Inside of you are the bugs that are down inside of your gut. And they're oozing out enzymes that are dissolving the organic matter, releasing the energy so you can blink your eyes and so that you can wiggle your hands. All of this, every beat of your heart is energy that was captured by photosynthesis of plants that lived in the soil. That energy came from the sun. You are an expression of sunlight energy. That's what you are. And you're just a big bag of wet rocks. And it's almost over, folks. And I don't mean my talk. I mean, it's almost over. And here we are in this moment actually talking about reality. This is reality. This is all that's real, really, is rocks dissolve in water. We're close to a star, and plants have figured out a way to capture energy and put it into tissues, and everything else follows from that. Everything else is a fantasy, actually. The only thing that is real is that. Those are facts, actual stone cold facts, okay? They can be, the observations on that, the measurements on that have been, replicated, the science, it's well known how this works, okay? And that, once you get that, you are free, man. You are part of this world and you belong. If you ever feel bad, just go outside, pick up a pinch of soil and say, 1 billion, and I belong. I belong to this planet. And that is why you should be growing food and eating food and hanging out with each other and making art. That's probably the only 4 things to actually, now hanging out with each other is a big category of things. Making art is a big category of things, right? But growing food, eating food, and the rest will follow, as long as you take care of the soil, because it's all about soil. And how the soil works is what I'm hoping to get to here at some point. But seriously, talking about the fundamentals, and these are the fundamentals, these are the facts that once you understand that, you can sort of figure out a lot of the rest. And and make sense of the observations that you make in your own garden or backyard or on a hike or whatever. So I do want to, ash all over the place. I do want to actually start my slides. And I promise they won't be super boring, because what we're going to do is we're actually just going to review a lot of that, but with some cool, look a little more detail. Okay. So it's all about soil. I think you got that right. Okay, good. Look at this. Here, I don't know, there's 20,000 different named soils, and they all belong to one of the 12 soil orders. Just like plants and animals have this hierarchical structure of how we taxonomically classify them, so too with soils. In fact, there's 20,000 different soils. They all belong to one of the 12 soil orders, and I'm not going to go through all of them, but I do want you to look at this one on the left. This is called an aridisol. And what do you think that means? Arid soil. It's a dry soil, right? And so do rocks dissolve in air? No, they don't. And so here it rains a little bit in the desert, just enough so that the salts move down one year, and then it rains later in the year. And then by the time the end of the year, maybe that salt gets down to about there, and then it stops raining for the whole summer. And then it happens again. Every year, a little bit of salt moves down about this far, but then it accumulates. And this is a layer of salt. It never gets to the groundwater. It never gets to the ocean. And so we have this layers of soil here that we call a BK horizon for carbonates. And look how thin the soil is. This is a cross-sectional view of a soil out in the desert, right? And that's like about 12 inches thick. That's as thick as the soil is. So it is a very small habitat. And I don't know if you can see this. I mean, if you live here, this is what you got to look like, which is these things are beautiful to each other, right? And there they are. And that's the sagebrush. They can live, and they figured out ways to live in really salty, low nutrient soils, because remember, not a lot of water, not a lot of nutrients are being released. And so the plants grow really slow, so we don't get lots of organic matter. Part of organic matter, of course, is roots. And all these plants live and die and live and die and live and die and live and die. But they do that a lot slower in an arid environment than they do in a moist environment. Over here, this is called a mollisol. And a mollisol, this is in feet over here. 2 feet deep, just the top surface soil, which we call an A horizon. But still, it as a topsoil. Maybe you've heard that term before. And the topsoil, this is where the roots of grasses have lived and died and lived and died and lived and died and lived and died and lived and died for tens of thousands, millions of years in some cases. And the roots, what are they? They're made out of organic matter. What's organic matter? Carbon from the atmosphere, energy from the sun. And they go down in and they die and they stay by. And some of them goes back to CO2, water vapor, and heat. But think about it. What stays behind is a little bit of that organic matter. Right? Think about it. How do you get a fire to burn hotter? You add oxygen. How do you add oxygen? Oxygen in, everybody. CO2, water vapor, heat out. CO2, water vapor, feel the heat on your hand. That's the energy of the sun from the food that you ate. And that's what you're doing. You're eating carbon, and you're putting it in here, you're burning it at a lower temperature because of the bugs that live inside of you. You're adding oxygen. That's an important part of the oxidation reaction called burning to happen. And then you're exhaling CO2, water vapor, and heat. And think about a compost pile. What's left over? The compost pile gets smaller. What's left over in the fireplace? Ash. So those are nutrients. So when a compost pile gets smaller, the concentration of ash or mineral nutrients is higher. And that's another reason we use compost in our gardens. But back to this subject. So that's all organic matter. So this is real powerful agricultural soil. And it's called a mollisol. And if you have mollisols, that's why we are here tonight. You know why we're here tonight? Because we have come from a place where there's more mollisols. See this in this scheme? This is a map of the global soil regions. Mollisols are in this green color, right? Look at that. 21% of the United States land mass is in mollisols. And worldwide, it's 7%. I mean, that's all you really need to know, is because we have these really great agricultural soils here. And those soils, you know how those form? Because of bison on the plains and grasslands. These are the grassland soils. And that's why we have this incredible agriculture here, is because we have this long legacy of historical connection between the bison, the people that were here, and the burning of these fields, and all that stuff happened. And that's what made these soils. These are 20 million year old soils here. And I don't know if you can see, look where the iridosols are. See the color, this kind of gray. Look over here. These are the troubled spots in the world. I mean, they who have the mollisols have the advanced technologies because they have the advanced agriculture. And agriculture begets the Industrial Revolution, and the Industrial Revolution beget the information revolution that we are experiencing right now at this very moment. It's because they're not doing this in South Sudan. They're not hanging out at 6 p.m. Tonight just to chat about soil. You know, they're struggling for survival in these parts of the world, right? All over. And I don't know if you can see, but there's one other nation on this planet that has almost as much mollisol as we do here in the United States. Can anybody see that? Yeah, Russia. I mean, this is it. I mean, they who have the mollisols have the intercontinental ballistic missiles. For good or for evil, this is why what you're really looking at here is a map of political power. That's where power really is derived from, is from soil and from that agriculture. And every beat of your heart is energy that was harvested from the sun by plants that lived in soil. And I'll tell you that these soil, the one on the right does that more efficiently than the one on the left. And from this soil comes what we know now, or we call, or whatever we call it now, civilization. I don't know if it's really all that civil, and wow, I don't know where we're headed, folks, to be honest with you, I really don't. So here's in the tropics. Have you ever seen the tropics, the soils in the tropics? Well, that must be really great with the jungles and all that stuff. Actually, they're really poor soils in the tropics because it rains so much there that most of the nutrients have washed away and gone into the ocean. And that's why there's sharks. And so there are these forests, these rainforests, where most of the nutrients are in the living biomass above the soil. And that's why the tropics are so incredibly diverse in their forests. Rainforests are so incredibly diverse because they're cycling those nutrients in the living biomass above ground. So I do want to show you something that you really need to know, because this is a really powerful thing. And I'm going to share a screen with you. If you could just Google this, you should all do this, or at least write it down. Google the California Soil Resource Lab, and it'll take you to the California Soil Resource Laboratory homepage, and here it is. And you go to Soil Web Apps, right? You can see this, Scott. Can you give me the thumbs up? Go to Soil Web Apps, and there's a whole bunch of different things you can explore here, and you should look at them all. Here's the Groundwater Banking Index, the Soil Series Extender, Explorer, Soil Properties, all this stuff. But what might interest you is to either Soil Web or Soil Web Earth. If you use Soil Web Earth, it downloads this little program down here, which installs it into your Google Earth. And now, I'm going to take us to Google Earth. In Google Earth, now we have this soil web. We have the layers of all the soils. The 20,000 different mapped soils are mapped here in the United States. And I'm just going to take you to Corvallis, Oregon, where I am right now, and show you the student farm. And I'm going to zoom to the student farm now, which is just on the east side of the Willamette River across from Corvallis, if you've ever been down here. And let's see. It works. Here is Corvallis. And what you'll notice is all these little, see all those lines? Those are the boundaries of various different soils. And like I said, and you could do this, put in your own address. and see what your soil is mapped at, because they mapped all the soils in the United States they started in the 1920s, actually in earnest in the 30s with the Soil Conservation Service. After the soil crisis of the 1930s, the Dust Bowl, Roosevelt said we are going to have a soil conservation service because it's about the nation's security. This is the fundamental resource for all of the future of all of the people who live on this land, is the soil. And so for the last 100 years, they spent their time mapping all of those soils, and you should learn about them. And here's where the student farm is. I'm going to zoom in on it. It's right down here, this messy little spot right there, right? This is all research, OSU research land. And we squatted on this land about 22 years ago. And they can't get rid of us now because we've been here long. They don't even know. They tried to throw us off the land 3 times. You know what we did? We just kept coming back. And eventually the people who tried to throw us off are have either retired or they're dead. Okay. And now we're still here. Okay. The kids, the future are the students. It's all about the students. And that's what I am so excited to do, is to teach students about the facts of life and how it really works. And it's all about soil. And if I just click right here, look, it's called Chehalis. It's one of the 20,000 different soils. It's a low floodplain group. It's actually called a cumulative ultic haplozero. It's a well-drained soil. And look at, here's a kind of a little view, a side view of the A horizon. This is all organic matter rich soil down to 51 centimeters. I mean, that's a thick A horizon because it's a mollisol. See how it ends in all right here? That's how we know it's a mollisol. And if I click on this, and you can click on anything that's blue in here, and it'll show you all this information about look at, here's the parent material. It's recently moderately fine textured alluvium derived from mixed sources. This came from floods. That's what alluvium means. This is a floodland soil. And you look at the native plants that are associated with this. So if you're interested in native plants, or if you're just interested in seeing what kind of plants grow here so that you can pick plants that will survive here, find out about these native plants and learn about, you can click on these and learn about each one of these native plants here. Here's the forest productivity. You can learn about how many board feet of Douglas fir you could grow on this. So all this information has been collected over the last 100 years and is available to every citizen in this country for free. Because there was this time in American history when people did this stuff for future generations. They wanted to actually build for the future. I know it was a long time ago. It's kind of in our misty past, but this is a relic of that time. And look down here. Here's the percent organic matter at depth, from 8% down, 8% organic matter down to 38 centimeters, etc. We'll come back to this later because I really want you to understand some of these things that are here, but I wanted to at least get us there real quick so we can look at that. So back to our slideshow. Can you see that, Scott? So we're good? Yeah. Okay. Let's see. So in Oregon, we have 10 of the 12 soil orders because it's such a diverse, geologically, it's a very diverse state. These are volcanic soils here in the Cascades. And then we have uplifted marine sediments from this, all used to be under the ocean and has uplifted. And then we have the Willamette Valley, which had these giant mega floods that happened here about 15 to 16,000 years ago. The largest floods ever to happen, have known happen on the planet Earth, happened here and brought in these very fine, loamy soils that have sand, silt, and clay. And that's why the mollisols are here in this scheme. They're a different color. But we have mollisols here. And that's why Salem is the capital, is because it's in the center of the Willamette Valley, which has the best soils. I mean, you think about where all the cities, the major cities on the planet are, and they're near rivers or old floodplains. And that's why those cities are there, because that's why the good soil is there. And the good soil is why people were there. And those cities grew because of that. where you don't see Salem-sized cities out, in Grant County, or, out here in Cook County, because these are mostly really dry soils out here. And so we don't have the productivity. Now, there's a lot of dry land irrigation or dry land agriculture and irrigated agriculture up near the Columbia. And those are very rich, beautiful places because of that. But we don't have all of the soil orders here in Oregon. We don't have frozen soils, and we don't have the tropical soils. Here's the spotosols on the coast. You've probably seen these before. These are ancient sand dunes. And what happened, look at this organic matter layer up here. And these leached, bleached, strong acidity, when these organic matters, when they dissolve, they create these very strong acids, which leach out the iron and aluminum, which precipitate out here into what's called a Spotic Horizon. These are like the charismatic soils. People travel from all over the world to come and look at the Spotic soils on the Oregon coast, believe it if you will. They do. And we just take them for granted. And when you go to the coast next time and you're watching the sunset, let me give you a little tip. The sun sets every day, okay? It's not that big of a deal, okay? What I challenge you to do, instead of watching the sunset over the ocean, is to turn around and watch the sunset on a spotosol. And you will see different colors emerge as the different electromagnetic spectrum frequency of the sun going down into the atmosphere, how it changes the colors on a spotosol. If you want to see something truly unique on the planet, that's what you need to have a look at sometime. So won't you do that? Andisols and entasols and septosols. Look, this is real soil. Soil doesn't come in a bag. Soil forms when rocks dissolve and accumulate these secondary minerals. And you can see this little crack right here? That crack is where there was once a root. And what is a root? It's carbon and energy. A tiny little root hair went down into the soil, and then it got bigger. And as it got bigger, it pushed the soil apart and made a large pore. And really, what you want in your soil are large pores, small pores, tiny pores, and super tiny pores. You want a wide pore size distribution. I don't know if you know this, but I'm going to stop this for just a second. You've all taken a bath, I assume, and check this out. You know that water, that little bridge of water, can you see that little bridge of water there? That small pores hold water against the force of gravity. And if it wasn't for that, there wouldn't be any life, any terrestrial life. That's the physics of it. That little bit of water can be stored there against the force of gravity. Even when it's not raining, there's water stored in small pores. And you know when plants need water at their roots? All the time. And large pores drain under the force of gravity. And that's why you want large pores, because then the water moves down and gets sucked into the small pores. And think about it. When a little raindrop is going down into a wormhole, what's being sucked in behind it? The atmosphere, air. When the soil is draining, the soil is breathing. It's bringing in air. And what do the billions in a single pinch need? They need air, just like you do, to oxygen, to oxidize the organic matter, to get the energy out of the carbon-to-carbon bonds in the organic matter. And that's why you need well-drained soils. But you don't just need well-drained soils, you need soils that hold water against the force of gravity. And that is because you have large pores, medium-sized pores, small pores, and tiny pores. And that's what you're trying to achieve in your soil management. And the more you till the soil, the more you compact the soil, the less large pores you have. And you shift it towards having more small pores, which means it stays wet and it stays cold longer. And wet soils stay cold, and it's all about soil temperature, about germinating seeds. And what you want are soils that drain well but hold water, and well-drained soils warm up faster. And so you get higher soil temperatures so that you can start your peas earlier. So trying to minimize the disturbance of the soil, because the soil self-organizes using the energy of the sun and the biota. The roots are sculpting the soil. They're going down and they're making large pores. And then when they biodegrade, they go away and they leave behind a casting of their roots. And you let that happen over and over and over and over for 10,000 years, and you have a mollisol, an agriculture. And if you till the soil, it just becomes more and more compacted, and it can't breathe. And so it becomes a poorer habitat. So you're trying to manage the habitat to have air and water in it, right? And so the way to do that is to simply minimize disturbance. If you just can I'm not saying eliminate it, but minimize it to the extent possible. And if you do that, and what's the answer? Add organic matter by adding compost, by growing cover crops, by leaving residues. You're feeding the soil carbon and energy, and the billions in a single pinch become more robust. And the more robust the system becomes, the more nutrients are being released, the more plants can grow there. And what are plants? Carbon and energy. And the more plants that grow there, the more they sculpt the soil to have large pores, medium pores, and small pores, and it becomes better over time. So good soils get better, where poor soils can become worse. And so if you just leave it alone, just leave it alone and keep the weed seeds out, it's going to get better. And then grow cover crops through the winter, because you're adding carbon and energy, and you're sculpting the soil to have a wider pore size distribution. You know what I'm saying? Right. So bottom line, again, soil is habitat. By any measure, the most diverse habitat on the planet Earth, a single pinch of which contains over 1 billion living organisms. And you know what? Most of those organisms breathe oxygen, and that includes plants. Who here has ever drowned a plant? Come on, you've all done it. If you're not killing plants, you're not growing as a gardener, okay? So don't worry about it if you've done that. But because the plants, maybe you don't know this, maybe you just learned tonight that they eat the atmosphere. You know what they breathe? They breathe at their roots. They breathe oxygen at their roots. And how do they get oxygen at their roots? If the soil is well drained, it pulls in air. So as the soil is draining, that's the ultimate measure of your soil management. Really, simply put, if you just put water on the soil and it goes in fast, you're doing it right. If you pour a bucket of water on the soil and it goes and it runs off, you're smothering all that. There's no oxygen's getting in there, and it stays wet and cold. And wet, cold soils have more disease organisms in it, because disease organisms are actually adapted to wet, cold environments. That's why your corn dies at the end of the season. That's why your plants die in your garden, because the organisms that can live at cold, wet environments eat them. I mean, that's what the fungi are doing. They're eating your plants. And as long as the sun is shining and it's warm, the plants can outgrow and fight off those aggressors. But once it gets cold, the disease organisms take over. And the wetter and the colder the soil is, the more of them there are. So I don't know, it's an awful lot of information here, and I know that. So just look, here's a single little tiny little piece of soil. Look, it's like a millimeter, maybe a half a millimeter by a millimeter high here. And look these are little pieces of sand. And what are sand? They're just rocks. And rocks dissolve in water. Look, in between, look at this, there's a little micropore here, right? Like between your fingers. And look, there's an ocean in there. And these rocks are dissolving nutrients into that ocean. And what's in there? A giant sea serpent is living in there, right? And that sea serpent is attacking these things, trying to eat them. Oops. And these things, these flagellated protozoa, they eat those things, but these things actually eat the poop of that thing. And there's a whole ecosystem going on between 3 pieces of sand right here. That's why the diversity of organisms is so high in soil, is because the habitat is so diverse. Look at this ocean of water. Here's an air-filled part of the soil. And look what's up in here, a completely different assemblage, a completely different ecosystem, a half a millimeter away. And look at this little ocean of water right here. And there's a root coming down here. And I don't know if you know this, but roots, they ooze out sugar water at their roots. Why would a plant give away photosynthetic production in the form of sugar? And all sugar is carbon from the atmosphere and energy from the sun, right? So they're giving that away. The plants are to feed the bacteria and the fungi. And why would they do that? Because the bacteria and the fungi can lower the activation energy necessary for the oxidation reaction called burning to happen, to release the nutrients from the organic matter. So right next to the root is where the highest biological activity is in soil, is next to the tiniest root hairs. That's why you shouldn't pull out your plants at the end of the fall, at the end of the summer rather. Instead, just cut them off. Leave the roots intact, leave the organic matter roots in there, and they will biodegrade out and they will make a wider pore size distribution and become better habitat to grow more plants, to add more organic matter, to make it a more wide pore size distribution. See how it works? It just happens because soil is a living thing. It's not a chemical sponge. Now in the 20th century, thank God it's over. The 20th century, we got really good at chemistry. And so we believed, we didn't know necessarily, some people knew, they were laughed at the university, I tell you. They were laughed at who believed in organic agriculture. But people said, oh, we can just feed the plants the nutrients directly. But kind of forgetting or not knowing, I mean, how long ago did we even know that there were a billion in a single pinch? I mean, not that long ago, honestly. And so nobody knew how this all worked. And here we are tonight at 6:04 or 7:04 rather, just hanging out, talking about reality. Soil is a living thing. If you get nothing else out of this tonight, soil is a living thing. And then now you know what you could do and what not to do. All right. So quickly reviewing, soil is rotted rocks, right? Rotted rocks and decomposed organic matter, but it's also space. The activity in soil is where it isn't. That's where the activity, it's in the negative space, because that's where the water is, that's where the air is, that's where the roots are, that's where the bacteria are, that's where all of the chemical reactions are happening. They're happening where the soil isn't. And so managing space, that you're not gardening, you're ranching microbes. You're not even ranching microbes, you're managing space. That's what you're doing. You're managing the space in the soil and managing it for a wide pore size distribution. So you have diverse habitat, so you have diverse organisms, so you have diverse functioning and efficiency of biological activity, which release more nutrients, that grows more plants, that captures more energy from the sun and carbon from the atmosphere and pumps it into the soil. That's a big part of the solution to our global crisis that we're in, climate crisis. 1/5 of the greenhouse gas emissions is from agriculture. And what we need to do is figure out how to get more carbon into the soil, out of the atmosphere. And how do you do that? You grow plants and you manage the soil to minimize the losses of that carbon in the form of carbon dioxide. And when you till soil, you're adding oxygen, which makes it burn away. You see how it works? But look at here. So here's like a little pie graph. How are we doing on time? We're all right for the moment? Yeah. Closest.
About 10 minutes. Now we should.
All right, no problem. So here's a pie graph of what soil is. Look, half of it is space. And depending on what size pores will determine whether there's air in that space in large pores, and in small pores, there'll be water. And you want about half and half because plants breathe at their roots. and they also take up nutrients in the liquid water at their roots. And that's why you need both. And then the other half is mostly minerals of different sizes, sand, silt, and clay. And then this little slice called organic matter. Get a soil test. You should get a soil test and find out what you have before you start dumping stuff on the soil. You need to know if you need to or not, or what to dump on, or what to grow there. Grow cover crops, increase the amount of organic matter. If you have 5% organic matter after you get your soil test, you're doing it right. And if you can maintain 5% organic matter and produce a lot of food, you're doing it right. But there are soils in the Willamette Valley that have 0 organic matter in them, 0% organic matter, because they don't leave anything left over, and the soils are now just minerals, and so they have to use more chemicals to farm. Or organic matter itself has nitrogen in it, and when it biodegrades, it becomes plant available nitrogen. And if you can maintain 5% organic matter, first of all, organic matter stores water 80 times its own weight in water it can store. If you can increase your organic matter by 1%, you can store 20,000 gallons more per acre water. And if you're paying for electricity to pump water, that's real savings. So maintaining organic matter itself, 5% organic matter will release about 100 to 150 pounds of plant available nitrogen per acre per year. That's enough to grow a lot of different things without adding any fertilizers. And then we're talking about this mineral, the mineral part of it, right? So this organic matter is the stuff that comes from the atmosphere and the energy of the sun. This is the dissolved or the partially dissolved rocks. So here's a rock, right? Remember zooming in on a rock, we can see the different minerals, and the salts dissolve first, and et cetera. And what happens is after these black minerals, which dissolve before the red ones, which dissolve before the white ones, and these white ones are just quartz, and that's what sand is. That's what's on the ocean. When you go to the ocean, you lift up the sand, is just all these white crystals. This stuff, this is quartz. And quartz is the slowest dissolving of all the minerals. And that's why it ends up on the beach, and that's what sand is. So once these other minerals dissolve away, you're left with sand, right? And sand is just anything from 2 millimeters down to 0.05 millimeters. That's all it is. It's just a rock. And a smaller rock is called silt, and that's 0.05 millimeters down to 0.002 millimeters. It's called silt. And then look at this. This is clay. Clay is 50 times smaller than the smallest pixel on the screen relative to these other particle sizes. And if you have, these are enormous range and size of particles, means that's what a loam is. It has equal parts sand, silt, and clay. And a wide range of particle sizes begets a wide range of pore sizes. And that's why a loam is good, because it's well drained and it holds water. Briefly, we have to talk about what clay is. Clay is not just a smaller rock. Clays form when rocks dissolve and then recrystallize at the surface of the earth. And the clay is a secondary mineral that forms at normal surface temperatures and normal surface pressures, and is the product of dissolution and recrystallization of primary minerals. And so primary minerals dissolve, and look what dissolves out of them. All these elements, right? Well, the four most abundant elements in the Earth's crust are silica, aluminum, iron, and oxygen, and they form these crystals that only can get a certain size, and they're called clay-sized particles, and they're clay. And when it dissolves, it forms these silica tetrahedrons and aluminum octahedrons, and this all gets put together into a crystal, and that crystal is what clay is. And you can see these kind of tinker toy crystals here. And on these crystals, based on the way that they're put together, based on the kinds of rocks, you end up with these negative charges on those clay crystals. And that is called the cation exchange capacity. When you get your soil test, you'll see this number. And the number of negative charges on your clay is measured at the laboratory. And you know what sticks to negative? And so soil is a negatively charged thing. And the more clay it has, the more negative charges on it. And you know what sticks to negatively charged things? Positively charged things. And you know what the charge on most mineral nutrients is? Positive charge. So when you're adding fertilizer to your soil, that fertilizer has a positive charge and it gets temporarily stuck to the negative exchange complex on clay. And that's what the CEC number, it's called a cation exchange capacity. And the higher that number is, the more valuable the land is because it can grow more stuff. And that's the difference between a mollisol and an iridisol. Mollisols have a lot of negative charge, so they can store a lot of nutrients, positively charged nutrients, which allows more plants to grow, which adds more organic matter, which adds more energy and carbon to the system, which feeds the biology, which makes the whole thing happen, which makes for a wider pore size distribution because there's more roots in the ground. See, this is the reason that you're alive, is because of the negative charge on clay. And look at, this is real clay at 100,000 times magnification. And it has net negative charges all over it. And that's where the nutrients are stored. And these are small particles. And small particles have small pores. And what's inside of the small pores? The water. And so the root hairs go in where the water is, in the small pores, where the nutrients are stored on the negative exchange complex of clay. And that's where the nutrients are, that's what the small root hairs are getting the nutrients, and the large parts of the roots are breathing oxygen from the well-drained soil. And that's why you want a distributed, wide pore size distribution. And all you have to do, folks, if you don't even know what I'm talking about at this point, is just chill out, don't disturb the soil, as much to the greatest extent you can. Just minimize disturbance, and all this just happens. It just happens. And that's why we're here, because it happened for the last 4.5 billion years. Last 4.5 billion years, clays that were made from dissolved rocks and an isomorphic substitution that created this negative charge. Look at these beautiful clays, right? All right. Turns out there's one other thing in the soil, I don't know if you can see it, that has that negative charge on it too, and that's organic matter. Organic matter itself has a net negative charge on it. Look at here, here's what it looks like. Look at, there is organic matter, a random molecule. It has negative charges all over it because it's a random molecule. So if you want to increase the cation exchange capacity of your soil, you don't go and get clay, you just add organic matter. And organic matter increases the cation exchange capacity of the soil so that it can grow more organic matter, so it can increase the cation exchange. And that's what soil building is. That's why there are mollisols. That's why you're hanging out here today, just relaxing and trying to understand what I'm talking about. Here's how a plant works. Plants are made from the carbon from the atmosphere. They push down, they make, look at, here's the big pore, the medium pore, and the small pore, right? They breathe oxygen at their roots and they exhale CO2 at their roots. Here's the liquid water is that dissolves the nutrients so the plants can take it up. And that's what a plant is made out of. And here, looking really close, here's a tiny little root hair zooming in on the smallest root hair you never saw. And look, it's in the small pore where the water is. And look, there's soil with a negative charge. Look, there's the nutrients that are stuck there. Either you fertilized or you added organic matter. Look, there's potassium, calcium, magnesium, right? Copper, they're all here and they're stuck there to the negative exchange complex. And the fact that plants exhale CO2 into the water acidifies the water, and that acidity actually knocks the nutrient off. And it flows into the plant, and that's how the plants get the calcium. And that's how and then you eat the plant, and that's how the calcium reorganizes into your body into a skeleton. Inside of you right now is made from calcium, and every atom of calcium that's in your skeleton right now was once on the exchange complex of clay and or organic matter and was taken up by a plant. That's what soil is, right? And if we look at this up close, here's all these nutrients that come from rocks, and some of them come from the atmosphere. And in the plant, they do different things. Like sulfur promotes reproduction, and calcium aids in translocation and photosynthesis from levels of fruiting organs. And potassium increases disease resistance, and all these different functions for all these different elements. And then we eat them, and they do much the same in us, right? And then, of course, all of this dies, and we all go back to the soil. And it is almost over, folks, and I am talking about my talk, because that's how soil works. And there's just what I wanted to just let you know again about this soil plugin for Google Earth. Go to the California Soil Resources Laboratory and see if you can find your soil and learn more about it. And if you really want to do something that really matters, I'm selling these t-shirts. That's right. This is all just a big soils pitch. A sales pitch. It's a sales soils pitch. And you can buy these shirts at soilforward.org, won't you please? We have them in ladies and gender neutral styles and all your popular sizes. I have them in hoodies as well. And I'm selling these shirts, and 100% of the profits of these shirts go to pay for my summer internships at the student farm. So I want you to think about the kids. Just get out of the way. Let them lead. It's their future, and let them learn about soil and support them by wearing this shirt. But I will warn you, you will wear this shirt, and I don't care where you are in the world. I've sold a lot of these shirts all over the world, and people will see you and they will say, "Saul!" And you'll go, "Yeah, down with the man," right? And it's just like, I've sold enough of these shirts to fund over 100 internships in the past 15 years. Okay. So won't you please? And just so you know, I also have them in Klingon and in Vulcan styles. That's right. Because Klingons, they eat a lot of meat. And where does meat come from? It comes from, they eat plants. And where do the plants come? It comes from soil. Same with Vulcans, man. They eat a lot of vegetables. Where does that come? It comes from soil. So won't you please go to soilforward.org right now and buy a shirt for the kids? Come on, get out of the way. All right, that's all I got for you right now, but I'd be happy.
Thanks, James. I got my soil shirt already. I got a couple.
I see that. No, I
buy them as gifts for friends and stuff too,
yeah,
so
please do.
you're always welcome.
And it's for the kids.
It's for the kids. We do have some questions. Of course, first of all, thank you as always. Getting us jazzed about soils, kicking off the soil school.
Oh, spring's here.
Yeah, we still have 7 more sessions after this, including our next session on Thursday at 6 o'clock is about soil health and the 4 principles of soil health. So,
who's giving that? Who's that?
That's Katie.
Katie Chambers.
Yeah, exactly.
She's I was a president of Oregon Society of Soil Scientists 3 times. And she is a member of the Oregon Society of Soil Scientists. So
yes, and can give a great presentation on the 4 principles of soil health. If you're interested in how you build a healthy soil, it's going to be the perfect, baseline, foundation for all of that.
I think you're really going to hear a lot of things that are going to help. The little bit that I set you up might actually help that information.
Yes, it builds off. I mean, the whole intent of soil school is like topics kind of build off each other too. So we do have a few questions here, and I'm just going to pull it up, and we'll start from the top here. Okay. First question we have, the highest rated, is if soils are mapped, why is it recommended that we have our soil tested?
Excellent! Wow, A+, gold star. You deserve a cup. Okay. And that is because, they map the soils to the best of their ability, but also soils have been, what the soil mapping is kind of what they should be or would be under natural conditions. And they change. And also where those lines are is, those are, if you look at those lines, they're like 80 feet wide, and it just doesn't go from one soil to the next soil. It kind of grades in. Some of them are quite abrupt, but some of them kind of, slowly become one or the other. So it's really important to not just completely rely on the soil web survey data. But what you should do is you should dig a hole, and about that deep, 2-3 feet deep, and then look on the soil web and see if it matches. And if it does match, then you can probably trust that data a lot more. But sometimes it doesn't. And sometimes there's just errors. And sometimes, you live in and in urban areas, it's not even mapped because they've always been urban areas. So it's called urban soils. And that's because a lot of the soils have been taken out, a lot of stuff's been brought in. So you really don't know until you dig a hole. Don't trust the web, trust your eyes, and then look and see how thick that A horizon is and see what the colors are like, and get a soil test and see if it matches up with the cation exchange capacity, etc. And if it does, great, then you can use that, you can trust that more. But if it doesn't, you kind of have to just talk to Scott and have him help you figure it out. Good question though. Wow, pretty impressive.
Yeah, and local soil and water conservation districts, as well as your local OSU extension, are great resources. If you have a soil test, go talk to them. Some of the laboratories even provide a little feedback on it. And
right, they'll kind of give you a high, medium, low on nutrients, like the A&L labs, I think, does that, and they'll give you recommendations. And it's just good practice to like look at the three, look at the soil web, look with your own eyes, look at a soil test, and kind of see if it makes sense or not. And if it doesn't, try and figure it out. Get someone to help you figure it out.
Absolutely. Next question. Have you seen Kiss the Ground? The documentary.
I have to say, well, let me say this. I assigned it to my students as a final once, as an alternative final, but I myself have not seen it. But don't tell them. I had the opportunity to see it at the last Oregon Society of Soil Scientists meeting in Bend when we were at the Worthy Brewing. And you should all become members of the Oregon Society of Soil Scientists, or at least come to our meetings because they're really fun.
They're fun.
And I didn't, and it was a long day, and I just went to bed. So don't tell anybody that I didn't.
Well, I will put a plug. I'm going to put a plug in. Our April 12th soil school session is actually a Q&A with, help me out, Christina. It's a representative from the sort of Kiss the Ground.
Yeah,
really?
Yeah. It's Don Smith. He is one of the educators for Kiss the Ground and worked on the film. So he'll be doing.
Wow. Well,
come ask all your questions on April 12th.
Well, I asked my students to be a little critical of it. I said, don't just, you've taken this whole class now. What do you think about this movie? And one thing that was very interesting that they said, my students said, is that they really didn't talk about different soil types. And that was kind of shocking. And it's also kind of Eurocentric sort of, agriculture and the way that, certain people think of agriculture. When really, worldwide, there's a lot of different kind of agriculture, small agriculture and different. So keep your eye out for that, but don't tell them I said that.
Okay, so
I haven't seen the movie, so just my students said that.
I'm sorry, Chelsea Bridges. I'm going to skip over your question because I feel like I got answered about soil surveys. And if you don't feel that it has, please reach out to myself or Christina or anyone else here. But I'm going to go on to this one. So it says, I've heard that roots left in the soil still absorb nutrients.
Oops,
is that true? And if so, how do we make sure that the plant can still access the nutrients needed?
I don't know about that. You mean after they're dead?
I'm assuming so, yeah.
Yeah, I mean, I guess maybe that there's some kernel of truth in that as they become biodegraded and become more residue organic matter, they can store nutrients, but they don't use them anymore. I don't think. So I'm not sure about that. Not quite sure.
Okay, how about this? I'm going to build off that second one, and I'll come back to Brenda's comment. You said to cut plants off and leave the roots to decompose. Will weed plants decompose or should one remove them completely, including the roots?
Well, there are many weeds are weeds because they're quite persistent, noxious weeds, and so you really should really think about that. I mean, there's a lot of weeds that aren't particularly bad. They outcompete your plants. I have like chickweed and some weeds like that I have in my garden. It's actually kind of a pretty good ground cover, and it's easy to pull up, and they die really quickly. Now, some weeds like quack grass, for instance, have a subterranean rhizome that stores a lot of carbon, energy, and nutrients. And the more you try and chop it up, it actually stimulates it to grow. So you need to get a book like Weeds of the West or something like that and really discern about different kinds of weeds. One of the most important things in weed control, though, is starting to get control of the weed seed bank that's in the soil. And by just minimizing the inputs, the deposits into that soil bank, by making sure things never go to flower. The minute you see flowers, you should cut that off and get it out of there, because it won't go to seed if it doesn't go to flower, many of these plants that we call weeds. And if you use cover crops religiously over the winter for years, pretty soon you'll exhaust the weed seed bank, because the seeds just can't last forever, and they can't outcompete a big, thick cover crop that's there. And so over time, and at the student farm, I have to say, after 22 years, we only have one weed that is a problem, and that is our quack grass, because it vegetatively propagates. But I'm telling you, it's thousands of times better than it used to be. And we've gotten to the point at one of our other sites, we really just don't have weeds anymore, but it took us 15 years of cover cropping, of minimizing the inputs of those weed seeds. But really, weeds there's a whole science to it. And there's the Weeds of the West book, if you've ever heard of that book, is something I would highly recommend.
Part of that question was where to get a soil test, and I posted an answer in the Q&A for the Oregon Analytical Laboratories. I will try to post that in the chat while I ask James the next question, which I just scrolled past. So give me.
And that website also tells you how to take a proper soil sample.
Yep.
What you want to make sure is that you take a random yet representative sample, which kind of doesn't make sense really. But if you think about it, in this screen that right here, if we were to actually randomize there's a probability, some probability, that it'll all end up over here, and that wouldn't feel very random, though it might actually be. So you want to try and get a random sample and then mix it together and send a subsample off to the lab. But they'll tell you how to do that at A&L Labs.
And that's really important. And also we always tell, I'm sure you do, different. So if you're out there on the ground and you see different conditions, different soil types, you want to try to get a different test for every.
Right, just different elevation changes.
Elevation.
Part of your garden is like this, and the other part's lower, probably a different soil. So you don't want to mix those together. You want to kind of get a subsample from that one and a subsample from that one and send those in separately.
Yep. Here's a good question. So you talked about soil organic matter is the answer. How much organic matter is too much? Especially for plants that might be.
It's only too much in that, especially the small garden, it's easy to do too much of anything because it costs a lot of money, right? And so people will buy, 10 yards of compost for a tiny little garden, and what you're kind of losing the mineral component of the soil. And that could be a problem for a plant to even stand up. It needs to be down in the mineral soil. So there's that. But beyond for larger acreage, maintaining 5% organic matter is not easy, and it's not cheap. So generally that's the number that we talk about is 4 or 5% organic matter. But you get 6 to 8% organic, it's still fine. It's not a big deal, really. But you still don't want to dilute out the mineral component. You know, you get to 20% organic matter, you're kind of getting into almost like a different kind of soil that maybe vegetable plants or certain plants aren't particularly adapted to. That, so there might be that too. So yes, in theory, it could be too much because it's just too different of a habitat for certain plants. And that's why you should just probably just hang around 5%, or, you know, as long as it's under 10, I suppose you're probably okay. But that's not a problem most people have.
Yep. Yeah, it's usually the opposite problem.
Right.
I'm gonna combine this last question into two, and they're not exactly the same. But do you have any great book recommendations for learning about soil? And do you teach any classes to the public? And is there a way that folks can take those classes?
Yeah, I mean, I books, you know, I mean, there's the big book, which is a really great book. And this is, you know, this is the elements of the nature and property of soils. But this is a textbook, but you will find it fascinating. I mean, you can get it used online probably for like $40 or something like that. And it, you know, it's probably a lot of it's gonna be way over your head, but a lot, but you can learn about the soil. But that's probably not the kind of book you're asking about, I'm guessing. You know, there's, what's that one? Soil Science Simplified. But that's just a little too simple, to be honest with you. But it's actually probably pretty good as an introductory book, because it does talk about soil texture, which is the kind of the percent sand, silt, and clay. Whenever I was kind of talking about that, and knowing what your soil texture is really foundational to the amount of water it needs, and the amount of storage and the amount of drainage and all that stuff is related to that. And it does talk about a little bit of everything I talk about. Soil Science Simplified. It's a very small book, but it's definitely something you should have. And I'm sure there's other great books these days, but that one's a simple one. You know of any, Scott?
Yeah, I'm trying to think of the one off the top of my head. There's a couple of good historical soil books. I'm trying to think of one.
Like Montgomery's. I got a couple of them here.
And when you want to learn about, you know, how, you know, other societies and civilizations.
Yeah, this one, Out of the Earth.
There you go.
That by Daniel Hillel, you know this one. And this is like civilization. This is like a lot of that stuff about prehistory and what civilization, and all these civilizations have come and gone. I mean, after the Dust Bowl, Roosevelt sent Loudermilk, a guy named Loudermilk, to tour the empires, the lost empires of the earth, civilizations. And he toured them all and tried to figure out what happened to them, why they didn't last. And all of them were because they abused their soils. And so that was very forward thinking on, and that's where the Soil Conservation Service got its start, which later became the Natural Conservation Service. But it's the same lineage, came from the Dust Bowl. And there's a whole there's a really great book called, how's that name of it? It'll come to me.
I will say, oh, sorry, go ahead.
Go ahead, no.
I was just gonna say, Annie from Tualatin just reached out and said on the Tualatin SWCD website, so you can Google Tualatin SWCD. They have actually a bunch of books on there about soils, and it sounds like a lot of those are on there. So a lot of good soil wealth. The other part of that question was, do you have any public classes outside of?
Yeah, I mean, this is kind of the extent of what my public outreach is. Although I'm happy to do intensives and stuff like that too, if you can just get my transportation or something like that, as long as it works out or something. And I you know, I'm online is not really my bag as far as like teaching. I mean, I don't mind. I like doing Zoom, but that's a kind of a different. That's more like a live performance. But you're welcome to sit in on my classes. In a fall term, I have a really great soils class, and if you're in the Corvallis area, absolutely, kidding me? But yeah, that's not so much.
Well, and I'll say, we'll be talking next year about whether we're going to do this in person again. I think our hope is eventually to go back into person. It's great, the accessibility of having Zoom, but at the same time, there's added benefits of doing this.
Oh yeah, so much more. I mean, I didn't get to see
Um,
anybody's face, and that's like half of it for me. It's like,
just my beautiful face.
yeah, I mean, you know, but you checked out a couple of times, there, Scott. I mean, I noticed that.
Some of us have to go to the bathroom. But,
Yeah, that's right.
so anyways, I definitely missed some of your questions. I'm going to throw my email in the chat for everyone. If there's any other questions that you didn't get answered that you'd really like to email me, and I will absolutely, if I can't answer the question, I'll forward it to somebody who can. So thanks again, James. As always,
And please,
brilliant.
please,
And,
why don't you go to soilforward.org. And that's actually where we sell our CSAs, we sell our vegetables and all that stuff. If you're in the Corvallis area, I actually have 5 shares left if you're in the Corvallis area. And you can learn more about what we do at the student farm there as well. But please, won't you?
all right. Well, thanks everyone. I'm gonna stop the webinar and the recording. But thanks again, James. I really appreciate it.
Thanks everyone. It was terrific. Really fun.
Bye.
I want that cup. That cup. I want a cup.